Hello, can everyone hear me? On Zoom, I assume is okay. I lied a little bit in my original talk title that I submitted. I am going to be talking about two things today. I'm mostly going to be talking about popIII feedback and how we can study it using ultrafaint galaxies. And I'm also going to be talking a little bit about neutral H1 gas in Milky Way satellites, so more massive dwarf galaxies and not ultrafaints. And I'm a postdoc at Yale, and I work with Earl Bellinger and Marla Jiha, and also the FIRE collaboration. So anytime I talk to an astronomer about popIII stars, I'm sure a lot of us have had this experience. This is the reaction I get. You know, like there's all these uncertainties. We don't know what the popIII IMF is like. We don't know what the supernova rates and energetics are like. We especially discuss, you know, what the yields might be like and how those might impact elemental enrichment in the early universe. And these are some of the things that I want to try to study using present-day ultrafaint galaxies, because as we know, it's practically impossible to directly observe popIII feedback in action. The reason I care so much about ultrafaint local group galaxies, for the purpose of this talk, I'm going to define them as having stellar masses less than roughly 10 to the 5. We're going to hear from Ethan next about what, you know, the very lowest limits of galaxy formation might be, but this is just a general rule of thumb for now. The reason I care so much about them is because they have uniformly old stellar populations, right? We are fairly confident that most of these galaxies, if not all of them, were quenched at very early cosmic times during the epoch of reionization or right after, and their star formation histories look uniformly very old. This is, if you're not used to seeing this kind of plot, it's just the fractional cumulative stellar mass assembly of the galaxy versus look-back time, and the gray band here indicates reionization. And as you can see from all of these Milky Way ultrafaint satellites, they all have very, very old stellar populations today. You can also see this present in Andromeda ultrafaint satellites, for example. And the idea is that because they formed all their stars at very early times, the stars that are present today in those galaxies should be the first or second generation of stars that were formed after the epoch of popIII stars. And so their star formation histories and their elemental signatures should contain imprints of popIII feedback. Another piece of motivation here is that if we look at the mass metallicity relation, the stellar mass metallicity relation in a wide variety of cosmological zoom-in simulations, we struggle a lot as a community to recover. We struggle a lot as a community to recover the iron enrichment that we observe in local group ultrafaint galaxies. On the left here, I'm showing FIRE results, older FIRE2 results, and there's a pretty significant offset, as you can see, in the mass metallicity relation for ultrafaints, and this is present in the EDGE simulations, DC Justice League simulations, and Auriga as well. Harley in his talk showed how some of this might be resolved using popIII feedback, and that could be explained if you inject a lot more iron at early times in these galaxies from popIII stars. All right, so for this popIII analysis, I'm working with the FIRE3 simulations. You've heard a lot about FIRE in a number of talks, but I'm just going to summarize a few updates from FIRE2 to FIRE3 that are relevant for my analysis. First of all, for star formation, we require that gas be genes unstable, you know, self-gravitating, but there's no longer a density or molecular requirement. There's an updated metagalactic spatially uniform UV background that reionizes roughly at around 7.5, 7.8 in redshift, which, you know, empirical constraints show from the CMB. And we've removed the initial temperature and metallicity floors that the gas is initialized at, which were previously 10 Kelvin and about 10 to the minus 4 solar. And on top of all of this, I'm testing my popIII models. For this talk, I'm only going to be talking about a very simple popIII model where all I'm doing for a popIII star is that I truncate the IMF and say that that star particle represents only massive stars above 8 solar masses. Right, so below a certain critical metallicity, you only have massive stars in your star particle, represented by the IMF. All right, so first of all, for vanilla default Fire 3 without any popIII model, this is what the mass metallicity relation looks like. And I want to focus here on the higher mass local group galaxies and show that even without the popIII model, we're recovering their iron abundances pretty well, not just the slope and normalization of the relation, but also some of the scatter. You know, some of the galaxies do scatter low here, but overall we're doing a fairly reasonable job with the mass metallicity relation. The question is, what are we doing here? And to answer this with my popIII models, I'm testing them on observers like to talk about wedding cake surveys. You can do the same thing with simulations where there's a trade-off between resolution and the mass scales that you're simulating. So I'm testing this in Milky Way mass simulations at a resolution of a baryonic resolution of about 7,000 solar masses. In simulations that model LMC mass centrals with associated satellites at between 100 and 1,000 solar masses, and in a simulation centered on isolated ultra-faint galaxies. And I'm running them all the way down to redshift 0. And with the isolated galaxies, you can really push the resolution, although it still takes a while. For this talk, I'm only going to be focusing on the middle set here, where you have a central LMC and then a number of very low mass satellites, including a lot of ultra-faints. So first, I just want to ground us in what the star formation histories of these simulations look like. One thing I'll add about the popIII model is that there's a smooth transition within a certain delta metallicity between what I'm calling a popIII IMF and a regular IMF, so it's not a step function, just to make things not look weird. But if I just track the number of star particles that the simulation volume forms over time, and this is just within the first gigayear after the Big Bang, you see that the regular vanilla star particles pretty much dominate after about 300 million years. But you keep having these bursts of popIII and those sort of transition metallicity star particles happen, and that's with the collapse of other overdensities that aren't quite as massive as the central overdensity. But in the central LMC mass system, you're quickly dominated by the popII and pop1 stars. All right, so now if I look at the ultra-faints in our simulations with the popIII model and what their star formation histories look like, about half of them exhibit this kind of star formation history, which is almost like comically cartoon pictured, right? Keep in mind that these are archaeological star formation histories, so they're based on what the ages of star particles that survive to present day are like, right? So what I'm showing here is just a single burst of star formation to get it to its present day mass, but that's a single burst of post-popIII star formation, right? The archaeological star formation histories don't tell you anything about what the popIII star formation is like if you believe that all the popIII stars explode before redshift 0. And the other half of the ultra-faints, sorry, the clicker's being weird, show more extended post-popIII star formation. Now, the interesting thing here is there does not appear to be a clear correlation between any of the things I've tested and what dictates whether an ultrafaint is going to have a very peaked star formation or more extended star formation. And that, that it's not governed by their final stellar mass, by their final halo mass, by the environment. And so there is an inherent element of stochasticity here in determining which galaxies will continue to have the gas to form further generations of stars. And how that imprints onto the mass metallicity relation, I'm kind of bearing the lead here by showing an extended y-axis. We definitely don't observe anything in the local group down here. I'm going to show you results from a range of simulations where I'm varying the threshold metallicity for what I call a popIII star by quite a bit. And I'm also doing a few other things like arbitrarily turning up the iron yields for the popIII star particles. That's what it looks like going from the least extreme models in dark blue to the most extreme ones in light green. And the takeaway here is that no matter how aggressive I'm being with what I call a popIII star or with what their iron yields are, none of that matters if all of that iron I'm producing at early times just escapes the galaxy, right? And so it really matters how much you're holding on to the excess metals you've produced by your popIII star particles. And I've taken a closer look at some of these systems at high redshift, and there's really dramatic evacuations of gas from the central galaxy corresponding to feedback from the popIII stars. And note, I haven't done anything to the popIII supernova energetics, the supernova rates. This is all with, those are all still standard Fire 3. So if you invoke more extreme supernova for popIII, this would just exacerbate this problem. All right, the one other thing I want to point out for one of our ultrafaints is that this also, these kinds of popIII models also imprint themselves pretty strongly on other elements, right? So I'm showing the metallicity distribution function, or the magnesium to iron distribution function for one of the ultrafaints, going from default Fire 3 in blue to, if I include the popIII model. And again, our model is fairly simple, but I think this is a valuable test because you get this dramatic magnesium enhancement in the present day abundances of this ultrafaint galaxy. And this is the sort of thing where the sort of measurements we get in the local group can provide really strong constraints on what models we might choose. And speaking of which, just last night, this morning on the archive, a new very metal poor star dropped. And this is claimed to be the most iron and calcium poor star that we have now confirmed in an ultrafaint galaxy around the Milky Way. Right? So its iron abundance has an upper limit of minus 4.63 spectroscopic. And in carbon over calcium versus calcium over hydrogen space, this star sits all the way up here, where there are a few known Milky Way stellar halo stars, but the vast majority of ultrafaint galaxy stars sit down here. Right? So once we start getting into this game of exploring multi-element space, you start to get really strong constraints on what feedback and enrichment models you might invoke. So in the last few minutes, I'm going to switch gears a little bit and talk about H1 gas in higher mass Milky Way satellites. This is work that's being led by a really fantastic undergrad, Grace Gagliatino at Colgate, in collaboration with me and Marla Jiha. What she's doing is comparing, disclaimer, this is now going to be Fire 2 results. Sorry, I'm jumping back and forth. But she's looking at Fire 2 galaxies in this mass range between 10 to the 7 and 10 to the 9.5, 10-ish in stellar mass, and those in Saga, because that roughly corresponds to the Saga stellar mass range, and seeing what the neutral gas content looks like in both of those data sets. The Saga results, at least as far as the neutral gas mass is concerned, were already published in Jiha et al. 2024. Right? You see this power law, maybe a broken power law, you might call it, but this is just neutral gas mass on the y-axis and stellar mass on the x-axis. And you actually see surprisingly good agreement with the Fire 2 trend here. This is not something we were expecting to see at this level. And I'll just leave this up here for a second. And I'll point out that we see some Fire 2 galaxies indicated by these downward pointing arrows that are way below the x-axis here. You would naturally not see them in your Saga H1 observations because they're way below the detection limits. But if you look a little closer at the Fire results, what's highlighted in red here are all of the galaxies that are quenched. And by quenched, I mean have not formed stars in the last 300-ish mega years, right? So take that with however many grains of salt you want. And notice that some of these red points are still sitting within the neutral gas M star trend, despite being quenched. So they do have significant H1 content despite being quenched. This is not something we have observational evidence for yet, although we just submitted a proposal to look at quenched Saga satellites and see if we can get upper limits on H1 there. And if you take a closer look now at the radial H1 distribution in all of these Fire galaxies, these are both satellites of the Milky Way and galaxies that are further out, so non-satellites, you get something that looks like this. You get this very interesting bimodality where you have half the galaxies with very radially concentrated H1 profiles and half of them with a lot more extended H1 profiles. And the color scheme is the same here to indicate the quenched galaxies in red and the star-forming galaxies in blue. And note again that there are some quenched galaxies with significant H1 content and also concentrated H1 profiles. So we're still looking further into what might be driving this bimodality in the radial H1 profiles. But I just wanted to present these initial results from Grace's work. So I'll just summarize and say ultra-faint galaxies are a really good probe of popIII star formation and feedback. And we're finding that, you shouldn't only be concerned about the yields of the popIII stars, but also about the feedback physics and how much gas you're retaining in galaxies at high redshift. And with Grace's work, we're seeing that as far as their overall H1 content is concerned, Fire and Saga galaxies appear to agree pretty well, although we're seeing some quenched but H1-rich galaxies in Fire 2. And we're going to look more into this bimodality in the radial H1 profiles. And finally, if I can have 30 more seconds of your time, I'll just add that it's a great pleasure to be here. Thank you for inviting me to this conference. And I want to highlight that we're all here doing astronomy, doing what we love to do, and there's a lot of people who want to be doing that but don't have the chance to do so for whatever reason. And two places where this is especially true right now is in Sudan and Palestine. So I'm just going to link some fundraising efforts for direct on-the-ground efforts there. Thank you.
Very nice talk. Do the quenched H1-rich galaxies have no molecular gas? Why are they not forming stars?
No, they do have molecular gas.
Okay.
But, so we're still looking into why they're not forming stars over the last 300 meg years, and whether it's, that molecular gas is fountaining and just hasn't sort of
reached the density to
collapsed yet. But yeah, it is interesting that there's also more extended, radially extended molecular gas in those galaxies, right? It's not just in the inner parts. Yeah.
Thank you.
A quick question while Ethan set up.
Excellent talk. So more of a clarifying question on your formation histories, the popIII, popII star formation histories you were showing. So you were showing the number of particles on the y-axis. Correct me if I'm getting this wrong, but you also, for the popIII particles, the average mass is probably higher. So in terms of the mass fraction of star formation, it seems relatively high to me compared to others. Maybe I'm wrong here.
That's a good point, and I don't have an exact plot to show for the mass fraction, but yeah, let's talk afterwards about it.
Thanks.
Yeah, thanks.
Let's thank our speaker again. Next, we have Professor